even though there's no change in energy in the system, there's no energetic input, this still happens spontaneously. And the reason is because S is going up. We're increasing entropy. Okay. So we've seen this a couple times. Now we'll actually use Boltzmann's statistical definition with it. Okay. Isothermal expansion of a gas. So if a system can convert to a higher state of multiplicity, it will do it. Okay. Equilibrium is where entropy is maximized. That's where it wants to go. The principle explains spontaneous expansion of a gas when there's no net input of energy. We don't need any energy input. This gas is going to expand to fill this entire space, driven exclusively by an increase in entropy or an increase in multiplicity. So entropy is a state variable that can be defined, right, in terms of multiplicity only. What was a state variable? Independent of path. Great. Yes, a state variable is that at any given moment, I could measure entropy of a system. It's not super easy to measure multiplicity of a molecular system in sort of in a lab setting. You wouldn't imagine how you could do that, but you can, in theory, for one state. Here you could calculate a multiplicity, here you could calculate a multiplicity, and I don't really care how I got between the two of them. I can take a difference in entropy. K sub B is still a constant. I'll take the difference in the natural log of multiplicity. Okay. Ideal gas particles have different configurations within the volume of a system. So picture these like our down molecules floating in our solvent. All right. We can go ahead and we'll imagine grid boxes that are small enough to define individual ideal gas atoms. Okay. I know that's not perfectly a realistic situation, but it works for our needs, okay? So in reality, there would be other components going on, but we're only going to consider position. Okay, so we have 6 gas molecules in 49 possible spaces. Okay, imagine dividing your volume into very small individual volumes, small enough to encompass just one gas particle. So what would be multiplicity for A? What goes on the top? How many spaces do I have to fill?
40.
How many gas molecules do I have?
6.
So my other option is either there's gas there or there's not gas there. It's yes or no, filled or not filled, a binary condition. Okay? So here's that. M is our number of boxes, N is the number of gas particles, and M minus N will be the number of empty boxes. And we'll get 1.4 times 10 to the 7th approximately. If we increase the volume, such as our expansion work condition, okay, let's say we go from 49 to M equals 98. In this case, the calculation is done with Stirlings because 98 is just about 100. Like I said, I will always tell you on homework or exams if I want you to use Stirling, but roughly when N is approximately 100 is when you should start using it to do your factorials. We calculate a multiplicity of about 10 to the 9th. It's an increase of about 100 times. Okay. So one way to interpret that is that it is 100 times more likely that the gas would expand to fill as much of the space as it could than to hang out on only half of it. Okay. It would expand to fill as much space as it possibly could, as opposed to concentrating itself on one side.